Now that I'm unmuted, today we've got two things on the agenda. We're going to do a volume of a solid of revolution, sliced perpendicular to the axis of rotation, on something where we know what the answer is supposed to be. We take this semicircle and rotate it around the x-axis. We know we're going to get a sphere. We know that the formula for the volume of the sphere is 4/3 pi r cubed. So our volume that we're going for is 4/3 times pi times 3 cubed, so 36 pi. Let's make sure that our process works out. Remember, the process that we're working with is we want to take the volume, or find the volume by taking the cross-sectional area and multiplying by the height. So our volume is going to be the cross-section area multiplied by the height. The cross-section that we're going to have here is a circle, and we're going to slice perpendicular to the axis of rotation. So here is a typical slice. We're going to take this segment, rotate it around the x-axis, and that's going to produce a circle. So the formula for the volume of the slice is going to be the area of the circle, so pi r squared, times a delta variable, delta x. So we want to go in and we'll label this radius. Anything that you start to label radius in this process should be is always measured from the axis of rotation. The delta variable is going to be some small change in x. And in this case, x is going to be the distance from the slice to the origin. Note that in this case, I didn't worry about which was the positive direction because we're working with coordinates, and coordinates tell us what the positive direction is. So we don't have to worry about where 0 is. The coordinates are telling us where 0 is. And we can see the values of x over which we want to integrate. We'll integrate from -3 to 3. So we don't have to worry about assigning a variable. The variables we have in this case, since we are on coordinates, have been given to us. In this situation, we can see that the radius is just going to be given by the function. So in our drawing, the radius is just equal to the function, the square root. Well, let's include all the things that I normally include. So notice I have x here, and here's another point on the circle. And so here is my y coordinate. When we're working with coordinates, we should always label where our coordinates are. So we need to write r in terms of x. It starts off with r in terms of y. So we can see that r is equal to y. But that's no good. Our delta variable is delta x. So we want to write y in terms of x with the function. So when we go to our volume of the slice, we have pi times the radius squared. So there's pi. The radius is the square root of 9 minus x squared, and then that gets squared. Times our delta variable, delta x. This is always our goal in these integration problems. Decide what the delta variable is. The burst over which we are considering things to be constant, that's the part that gets smaller. And so everything has to be written in terms of that variable because we've decided to play the more difficult game of single variable calculus. Now we can find the total volume by just adding up the volume of the slices. On our usual fashion, we totally skip over the Riemann sum. Sorry, Riemann, but we need to get to our definite integral. We are going to simplify our expression. Square root of 9 minus x squared squared will just get simplified to 9 minus x squared. Our delta x, our discrete delta x for each slice becomes the continuous dx in the definite integral. And then we just have to integrate wherever we see an x value. And we have a slice when starting when x is -3 and ending when x is equal to 3. So integrate from -3 to 3. Although I didn't write it because I was just writing this problem, I will typically frame these by saying, show your calculations, which just means write the definite integral that you're going to be integrating. And write down the volume of the slice. I don't want to see you actually integrating. That's for a different quiz altogether. So we'll just use a machine to find our integral. We'll math 9 minus x squared with respect to x from -3 to 3. I had the wrong parentheses. Must have hit that. And 36. That's the integral part. It gets multiplied by pi. So we get 36 pi, just as we suspected. Then you try to put 36 pi into Canvas, and it's like, oh, no, you need to round that to the nearest to 5 significant figures. So we would just write 113.10. Note that 113.10 is different than 113.1. If I say 5 significant figures and you write 113.1, you have written 4 significant figures, and I asked for 5, and I will not count that as correct. I'll say 5 significant figures. I want 113.10. Usually what happens in this kind of problem, I also include 113.09. So I also have the truncated answer. Even though I said round 5 significant figures, I usually allow you to truncate at 5 significant figures as well. But I want 5. If it's written and you're handing it in on paper and you write 36 pi, that's fine. That's probably what I'm thinking of anyway. Any questions? So the important thing is that our process led to the expected result. So if I change this to something other than a semicircle, we have a little more faith now in the process. We have a little more experience in setting up the definite integral, which is the point of the problem. Finding the volume of the sphere, not the point of the problem. Understanding how to set up an integral and doing some analytic geometry, that is the point of the problem. questions? So there's another way to find the volume of a solid of revolution. We make discs and washers when we slice perpendicular to the axis of rotation. So we can also slice parallel to the axis of rotation. This is going to be slicing our solid into cylindrical shells. We're going to slice our solid into cylindrical shells. The cylindrical shells are actually going to be rectangular solids. The delta variable will be the thickness of the wall of the shell of the cylindrical shell. The delta variable is going to be how thick the wall is, and the length is going to be the circumference of the cylinder. So what we're going to do is we're going to have our cylinder and we're going to unroll it into a rectangle. Our cylinder has a radius of r. And a height of h. We're going to take our cylinder and unroll it into a rectangle. When we unroll the cylinder, the height is going to be the same, but the length of our rectangle is going to be the circumference of the cylinder. So if the radius of the cylinder is r, when we unroll our cylinder into a rectangle, the length of the cylinder will be 2 pi times r. Right now, we just have an area. So we turn this into a volume by imagining our cylinder not as a two-dimensional surface, but as like an actual piece of paper that has a thickness, or a can that has a thickness. or a piece of PVC pipe that we're going to unroll. I don't think you can unroll PVC pipe. Let's take a cylinder of metal that we can cut and unroll. So the cylinder is going to have some kind of thickness to it. So there's going to be like the thickness of the wall of this cylinder, and that's going to be our delta variable. So we can take our two-dimensional surface cylinder and unroll it into a two-dimensional rectangle, or we can imagine some kind of thickness of the wall of our cylindrical shell. And unroll it into a rectangular solid. So when we are slicing parallel to the axis of rotation, the volume that we're going to use is going to be for this rectangular solid or this cylindrical shell. The volume of the slice will be 2 pi times the radius times the height times the delta variable. So length, width, height. You may notice that the insides of the cylinder is smaller than the outside of the cylinder. But if we make the cylinder thin enough, we can still unroll it. So even though the inside cylinder of a Coke can is smaller than the outside of the cylinder of a Coke can, if you cut the top and bottom off, you can still unroll it. That's why this line over here is a little bit wobbly, because there's going to be some deformation as we unroll our cylinder. I recently learned that beverage cans are not actually aluminum containing it's actually in a bag. The Coke is like in a plastic bag. And the plastic bag is in the can. If you melt all the aluminum off the can, the Coke will still be contained. And that's how I found out that Keystone, the beer, that's what they were talking about when they were keeping their Keystone beer from tasting like metal. How did I get all the way through college before I learned that? I don't know. What are we talking about? Oh, yes. So if we slice parallel to the axis of rotation, we're going to use 2 pi r times h times the delta variable. Any questions? Let's do a problem. So at this point, if you didn't see it coming that I was going to do the same volume on the slice parallel that I used for the slice perpendicular example, that I don't even know. It's like you're not even, do you even go to my class? It's always something that we know. And if there's two methods to do a problem, you know I'm going to do them both. Pens can be so picky. They can't write at certain angles. And these pens have a speed limit as well. So we want to find the same volume. We know the answer is 36 pi, but we also know that finding the volume of the sphere is not the point of the problem. We're going to make a slice and it's going to be parallel to the axis of rotation. So here, instead of slicing perpendicular to the axis of rotation into delta x, we're going to slice parallel into a delta y. So our slice is going to go this direction. So since this is going to be the thickness of our wall, we've sliced into a delta y. The variables are going to be the same as we had in the previous problem, except with a twist. There's going to be a y coordinate, but each y coordinate is going to correspond to two different x coordinates. Since we're finding the volume of the solid of revolution and we are slicing parallel to the axis of rotation, we know that our volume of the slice is going to be 2 pi times the radius. All right, the volume of the slice will be 2 pi times the radius times the height times the delta variable, which in this case is a delta y. Now that I know what I'm looking for, 2 pi radius times delta y, I need to go on to my picture and I need to label what the radius is, and I need to label what the height is for our slice. The radius always has to be measured from the axis of rotation to the slice. So that means that our radius has to go here. From the axis of rotation up to the slice. That means our radius, r, is equal to y. We're trying to write this problem in terms of y, so that works. R is taken care of. Our height for cylindrical shells is always going to be perpendicular to the radius. So our height is the difference in the x values, x2 minus x1. This is no good. I need these in terms of y, not x. The relationship we have between y and x is that y is the square root of 9 minus x squared. So if we solve this for x, we get that x is equal to plus or minus the square root of 9 minus y squared. So it looks like x2 is going to be the positive square root of 9 minus y squared. And x1 is the negative square root. So it looks like our height is 2 of these square roots of 9 minus y squared. Now I have the volume of my slice all in terms of y. Now we've finished our development phase. We can move on to the definite integral phase for our volume total. This is where we will usually take the opportunity to simplify our expression. I've got 2 pi and a 2. That's all constant. I'm going to pull a 4 pi out front. And then we'll have the integral of y times the square roots of 9 minus y squared. Our discrete delta y becomes a continuous dy. And we have to integrate over all the appropriate values of y, all the values of y for which we have a slice. Now, in this case, we're integrating over the y values. So y will go from 0 up to 3. Down here at the x-axis, that's where y equals 0. And up here at the top of the circle is where y is equal to 3. Even though this would be a nice, simple integral to integrate, we've already done the thing where you've shown me that you can integrate by substitution. So we're just going to math 9. So math 9, y times the square root of 9 minus y squared with respect to y from 0 to 3. So we get 9. But this is all being multiplied by 4 pi, so we get 36 pi, just as we suspected. You may notice that your calculator did not exactly say pi. My calculator is like on 9 point, a bunch of zeros, then 355. This is your calculator trying really hard to say 9, but it's carrying too many digits. So I think this is just your calculator flexing on how many digits it can carry around.
I've got plenty of digits, man. I could display that for you.
But it's approximating. So we're going to have to read that as 9. Question? I took the inverse and I found the inverse. And when finding the inverse, I had to do a square root of x. When we do a square root and we're solving, that produces the plus or minus. So I didn't multiply by 2. I took this positive one and subtracted a negative one, and that ended up being a 2. Because of the symmetry, we could think of multiplying by 2, but that's technically not what I did. And we all know that technically correct is the best kind of correct. Any questions? I think it's got, how many digits does this have? So you can see it goes a lot farther than the 355. Oh, I've got more than that. But it's like times 10 to the negative 7, so. Your calculator's like, oh, I have more details. And you're like, oh, dude, I don't want more details. This would be like stating your weight in grams. Down to the nearest unit. Oh, I'm sorry, you are 10 grams over the weight limit for this particular thing. Okay. How about now? Okay, now you're okay. I mean, that's why you don't weigh yourself in grams. Oh man, I gained weight. What happened? I ate a strawberry. This is the main event. Any questions? So I like to categorize our solids of revolution as slice perpendicular or slice parallel. Slicing perpendicular. Will produce discs or washers. Discs are going to be pi r squared times your delta variable. Washers are going to be pi times the difference between the squares of the radii times your delta variable. And then over here, we've got slice parallel. And the volume of the slice will be 2 pi times the radius times the height times the delta variable. You get discs if the axis of rotation is a boundary of the region. And so all you need is one radius. You get washers if your axis is not a boundary of the region. And that's why we have 2 radii. One radius to the near side of the slice and one radius to the far side of the slice. We get cylindrical shells if we slice parallel to the axis of rotation. The radius is always measured from the axis of rotation to the slice. And for shells, the height of the slice is always perpendicular to the radius. The generic 2 pi radius height delta x is because we can slice parallel or perpendicular delta x or delta y. The example that we did, since our axis of rotation was horizontal, perpendicular was a delta x and parallel was a delta y. But if we have an axis of rotation that is vertical, perpendicular will be delta y and parallel will be delta x. Any question? How's everybody okay? What this means is that if you're finding the volume of a solid of revolution, you should always do the problem twice. One with parallel slices and one with perpendicular slices. Tomorrow we'll do an example where one method will be more convenient than the other method. And it'll be artificially complicated for some reason. Normally I do a parabola because it's not invertible on a particular interval. And usually I have to switch my parabola around. A lot of times I'll use 6x minus x squared, but then our natural default is to slice delta x anyway. So I switch it around to 6y minus y squared, just to be difficult. All right. You should keep in mind that the integration thinking that we've had in these solids of revolution has been mostly the same. The stuff that we're doing now is less calculus and more like analytic geometry. So if you're like, oh man, I thought I was good at calculus, this is confusing. It's because you're doing analytic geometry, and that's the skill that we're working on right now. So don't worry about it. Just do some problems. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.